Thank you. I was thinking of speaking in English in deference to our guests and having my transparencies in Spanish in deference to my hosts. And is that all right? Okay, then as a physicist, I start by doing some tests of these things that never work. And it seems to work, sort of. Stopped working already. Now, this is an alternative possible title to my talk. 10,000 and some physicists departed towards an unexplored world. And imagine that you were really not coming from down Santa Cruz or whatever, but from a completely different universe with different laws of nature and different everything. And you were getting close to our planet with your usual means of transport, and you were guided by some map, maybe drawn by some extraterrestrial Leonardo, such as this one, and you were getting to a country where there are plenty of cows, obviously, and you would be seeing at a certain moment this picture here, in which you see, is this functional? Of course not. Can anybody make this laser light work for me? Thank you. You would see Lake Geneva down there and the Mont Blanc 80 kilometers away. And if your technology was sufficiently... Okay, thanks very much. If your technology... Oh, it's so small. If your technology was sufficiently good, you would detect that there is something circular underground, 27 kilometers long, over there. Now, this is another picture of it, where you see Geneva Airport, and something that you would definitely think is difficult to detect is this line of points, which is the frontier between France, which is in this side, and Switzerland, which is in this side. If you get a little closer, the frontier is very evident, because on the Swiss side, every garden is full of beautiful flowers, well tended, and in the French side, you have these old cars in the yard rotting, and so on. So it becomes much more obvious when you get a little closer. Now, this is a scheme of what is underground around there. There is a tunnel which is 27 kilometers long, as I said, and this is some sort of Swiss clockwork. It's an accelerator that accelerates protons on two different directions to have them collide. But the protons come from a series of pre-accelerators, starting here, some of which are 50 years old or more, like this one called the proton synchrotron. And in a series of more and more energetic accelerators, the protons are finally injected into one or the other direction into this very large collider. Now, in order to build a collider, you first have to build a tunnel, and you rent some machinery, such as this one in here, and you go under and start digging. This guy is obviously Spanish, because nobody else but a bullfighter would stand in front of this machine and happily be doing something there. And finally, you construct this tunnel, which is about 3 meters high and 27 kilometers long. And it goes from nowhere to nowhere because it's circular. It's the dream of the current Minister of Justice and former mayor of Madrid, who made all these tunnels that as only purpose have putting fines to speeding cars. And that would be ideal. But it isn't full of cars, it's actually full of machinery. And the machinery is essentially a long line of magnets. This is one of those magnets. They have a length of about 17 meters, and we'll be seeing them in more detail. And every now and then, around this circle, you build a very large cavern. Here is one of those caverns under construction. And here is one slightly more advanced, and you see there's a tunnel which is about 60 meters high that connects to the surface. And from the surface, you're going to bring the apparatuses that you're going to fill this thing with. And this is another tunnel, this time almost finished, very clean. And you see there a word, well, maybe you don't see it, it says dragados, which means that Spanish technology actually participated in this, not very advanced technology, they just made the hole. And here's one of these caverns once it's built. This is, of course, only a design moment in this operation. And you have in here a couple of people to give you an idea. These are normal people from the Canary Islands. They are no giants and no dwarfs. It gives you an idea of how large this object, which is essentially a camera, is. Now here you have a more advanced period in the construction of the detectors of the collisions that are going to be produced in this machine. This is called the end caps, and they have been put down through this hole with about 1 centimeter on each side. It was a very interesting operation. Everybody was very frightened. And again, you have a couple of people here to give you an idea of the size of these things. Now I'm going to turn this thing around and put it in the direction in which the protons will be coming from one side or the other side of the tunnel through a hole which is about this size in here. And this will be the size of the tunnel. The tunnel doesn't get all the way in, only the tubes in which the protons come in are coming all the way in. And I cannot, I'm drawing there again the size of the tube that goes through the middle of this apparatus. And I cannot draw how large the beams of protons coming from each direction are in cross-section, because the cross-section is about 1/10 of a human hair. Now, this is a next section of the construction, a next moment of the construction, which is made from outside to inside. This is where the inner part of the detector is being put into the center of the detector. Again, a couple of people here to show you the size. And you see this is very reminding in the amount of effort, tens of thousands of people working for decades in order to build something. And historically there is a similar kind of enterprise, which was the building of the cathedrals. In Barcelona it's still the building of the cathedral. And the difference is that they used to put them outside, but we put them underground. And the reason why we build these enormous things, which are the highest technology and the biggest machinery anywhere, and maybe the most beautiful objects, the reason why we put them underground is that physicists are particularly modest, as you can see in here. Now, this is also a design of how there are various experiments. There are 4 large experiments called CMS, ALICE, Atlas, and LHCb at 4 different positions inside this panel. And this is 2 of them seen above the position where they actually are, and this is the 2 others. And this is to give you an idea of some of the sociology of this enterprise. This is a list of the 10,019 people that I quoted at the beginning of my talk, listed by country. And you see there are about 70 different countries, about 150 different languages being spoken in the cafeteria at CERN. And there are 330 Spaniards out of 10,000 people. There are 3 times as many Russians, 1,027, even though Russia is not a member state. The member states are these in here. Russia is an observer. There are more Russians than Americans, only 892 Americans. And there are people from really everywhere, like 3 from North Korea and 85 from South Korea. There must be a reason for the difference in numbers. And the very curious thing is that there are 1,700 Italians. How comes the fraction of Italians is so enormous? There are various theories of that. The Italian theory is that they are better, superior, more intelligent, and therefore that's it. Now, another theory was advanced by Pope John, who on one occasion was asked, "Your Sanctity, how many people work in the Vatican? And he said, less than 50%. Now, how does this accelerator work? It works in the following way. It has two essential ingredients. One is called a high-frequency cavity, and it's shown in here. There are, I don't know how many, maybe 600 of these things around the tunnel. And what they do is the following. As a proton in one of the proton beams approaches the cavity, the proton is a particle with a positive charge. The cavity is negatively charged and therefore attracts the proton and gives it a little extra kick in energy in the direction of flight. And when the thing goes to the other side, if it does, then the polarity of this thing is changed to plus, so that it now repels the proton. So every time a proton goes through one of these little holes, it gets 2 kicks, and it gets to a slightly higher energy. And that's the accelerator part of it. And then there is the rails, like in a railroad track, that keep the protons in one direction and the protons in the other direction in their roughly circular orbits. And that's achieved with magnets. This is a picture of the magnet on the right and scheme of the magnet on the left. The magnet has 2 holes through which the protons go in one direction or the other, and there's a magnetic field in opposite directions in these 2 holes. And that's because if you have a particle going one way and a particle going the other way, in order to bend them both towards the center, that is to say to keep them in a circle, the magnetic fields have to be in opposite directions. So that's the railroad track. So you have protons going in both directions, and unlike in a conventional highway, these 2 lanes cross at 4 different points, which would be dangerous in an actual highway. And because, of course, what happens is that there are collisions in these intersections, and it is the product of the collisions that are particles that are created in the collision by the conversion of energy into the mass of the new particles. That's what we study, and that's what gives us a way to investigate how nature works at the highest energy, which corresponds to the smallest distances we can study. This is a phone not for me, and please say I'm busy. This is the first collision that was achieved one day in this machine. And again, for a little bit of sociology, you see here the reaction of the people looking at the screen where this first collision in their experiment is shown. And there's a lot to say about this picture. For instance, Madame Merkel is here in the middle. And you can also see that most people are enjoying the moment. And these are the only 2 that were working all night to have this thing actually function. And one good question, this is a question posed in Spanish, is why do we do all this? And the reason why we do all this is that we want to know what things are. That is to say, there's stuff around here, and we want to know what it is and how it works. And you all know that if you look at your hand with very good precision, it's mainly made of water, which is a molecule that has 1 oxygen and 2 hydrogens. And the hydrogen, which is the simplest of atoms, is made of a proton and an electron. The electron is what we call an elementary particle, in the sense that if it is made of smaller objects, we don't know. It behaves for all intents and purposes as a point in space-time in the manner it interacts with other objects. And the proton, on the other hand, is not an elementary particle. It's made of 2 quarks. 2 of them are called up quarks, and 1 of them is called a down quark. And these particles are also candidates to being elementary particles. That is to say, they have no parts as far as we know. And there's another object that constitutes the nucleus of oxygen, and that's a neutron, which is very much like the proton. It's made of 2 down quarks and 1 up quark. Now that is a little bit of what things are. We also want to know how things work. And here you have a neutron that, as I said, is made of 3 quarks. And if you have a free neutron, it will decay after a while, as time goes by, into one of its down quarks decays into an up quark to make a proton in the final state. And the collision, the process also made 2 particles extra. One of them is an electron that I already named, and the other one is a particle very much like an electron but without an electric charge, called a neutrino. And we haven't seen this guy before. What is it doing? Well, if you want to construct a rocket or an apple or make a pizza, you only need 3 ingredients: and up quarks, down quarks, and electrons. Up quarks and down quarks are very similar except for charge and mass, and the electron and this other object, the neutrino, are also very similar except for charge and mass. And the first question to ask is, why the hell are there neutrinos if you can't make cheese with neutrinos? And the reason is this here. Is a very good year for this particular wine. And the reason is that without neutrinos, there would be no wine. And that's because the sun, this transparency happened to be in French for some reason. The sun is an oven that burns 4 atoms of hydrogen, that is to say 4 electrons and 4 protons, through some reactions that I'm not going to read. And the end process of this reaction is an atom of helium that has 2 protons, 2 neutrons, and 2 electrons. And if you count the particles, 2 are lacking. The 2 that are lacking and not lacking are actually 2 neutrinos that come out from the sun with about 2% of the total energy. The other energy produced in these reactions ends up as radiation of light from the surface of the sun, and that's the rest of the percentage. It takes the neutrinos 2.3 seconds, they'll travel essentially at the speed of light to get out of the sun. It takes a photon 1,000,000 years to get out of the sun because the photon interacts very much with electrons and has this complicated path. It takes it forever to get out. Both neutrinos and photons take 8 minutes to get down here. And while we are talking or listening, some of you, but I hope, about 60 billion neutrinos per square centimeter per second are crossing your heads from the sun. And therefore, this is the syllogism. Without neutrinos, the sun would not shine. Without the sun, there would be no wine. And corollary, there would be no wine without neutrinos. So the neutrinos are absolutely essential to mankind. Now, this was a theory for many years, but it isn't. For 15 years, we know that this is not only a theory, it's a fact. Because of this picture, which is the most important picture of the last century, this is a picture of the center of the sun, about 1/10 of the radius of the sun, which is the core of the sun in which these reactions are producing neutrinos. And this picture is actually a picture. It was taken with a camera which is underground in Japan. It's 10,000 cubic meters of water. This is when they were filling it. And once it is filled, the neutrinos from the sun occasionally interact with the water to kick one electron to higher energy. And that electron moves in the water and emits a light that is seen by these objects that are photosensitive. And they tell you where the neutrino came from, what energy it had, and so on. So this is an actual, it is not a photography, it's a neutrinography, the thing that I showed in the previous transparency. We are in trouble here. No. Yes, this is what I wanted to show again. Now, I've been telling you so far about up quarks, down quarks, electrons, and with what I will now call the electron neutrino. The reason to give a name to this guy is that there are almost identical copies in nature of this, which is called the first family, the second family, and the third family. And these objects are also not useless. I don't have the time to explain today why these things are also necessary. But the only difference between the guys of one column and the other column is the mass. This quark that was invented by Shelley and is called the charm quark has identical properties to the up quark, except that it is heavier. And as a consequence of that, it's unstable. It decays into particles of this generation. And there's another one called the top quark, which is again identical to the previous one, only heavier. And that's true along the other lines as well. So one essential question that we are going to ask ourselves is, since the thing that distinguishes one guy from the next is the mass, what is the origin of the mass of these objects that makes them different? It's like their name, like the family name is the mass. And that's the question. Now, suppose we took this room, which is filled of people. I'm assuming people were polite and let the ladies sit in front. And I take these people out, and then I take the air from the room out, down to the last molecule of air, and I cool the walls to 0 temperature so that there's no radiation. So after a while, I have made, by definition, a vacuum. There's nothing else here. Now this is not quite true, because even once you are all the way and there is no air in here, no light, I would still know that there is a substance in this room that is affecting me, which is the gravitational field of the Earth. I cannot see it, but I definitely know that it is there, because if I drop my glasses, they will drop. So there is a field, a substance, permeating this room, even if I took away everything I can take away. I can also take away the gravitational field, because I now take the room and put it very far in space in a place where the gravitational field is negligible, and then I have a truly man-made or woman-made vacuum. Now it so happens, and this is very interesting in my opinion, that the vacuum is a substance. The vacuum is not nothingness. It's not empty. El vacío no es la nada. And it's also permeated by a field, which we call the Higgs field, and name phi, and its value in the vacuum, which is this symbol 0, is not equal to 0. So there's a substance permeating the vacuum of the universe, we very convincingly think. Now it is this substance that is responsible for the various masses of the particles that have mass. If I throw through the vacuum a particle which is light, it interacts very little with the vacuum, and that is what makes its mass small. If I throw a particle, for instance, with the same energy, which is heavier, it's heavier because it interacts more intensively with the vacuum. And it is the vacuum that, in interacting with the different particles, does it in a different manner for each type of particle, and that's the origin of the different masses of the particles we very much believe, for good reasons. Now, if the vacuum is a substance, as I have argued, then you can shake it. And when you shake something, it vibrates. The elementary vibrations of the vacuum are elementary particles, and that's the particle which is called the Higgs. The Higgs is the quantum of vibration of the substance of the vacuum, which unfortunately we call the Higgs. It should have another name, for instance, tokenon, which would be more sophisticated, because kenon in Greek means vacuum. And as far as I am concerned, the LHC stands for MSV, that is to say, a machine to shake the vacuum. Una máquina para sacudir el vacío. And why do some people call it the particle, the God particle? Now, there used to be a reason for this, which is no longer the case. And the reason is the following. My brothers and sisters, both about the vacuum, about the Higgs boson, and about God, we know everything except whether or not they exist. Now, in the case of the Higgs, the question can be decided, and has been decided. It does exist. And the way this was proved is by making these quantum fluctuations of the vacuum, called the Higgs boson, in collisions between protons at the LHC. And the dominant process for that is fairly complicated. The proton has particles that are quarks that interact with what glues quarks in a nucleus, which are also particles called gluons. And those gluons, through a loop of top quarks, which are the heaviest, and therefore the ones that most interact with the Higgs field and with the Higgs boson, make occasionally one collision every many billion, trillion, I should say, make a Higgs particle. And the Higgs particle decays through a similar process in ways that you can detect. For instance, it can make two particles of light called photons, and this is one of the first examples in which two photons, candidate objects for being the decay products of the Higgs particles, were made in one of the two experiments. This is the deposition of energy in certain detectors that are called calorimeters. The thing is coming from the collision point, which is here. And this is the first evidence for a Higgs particle being there and decaying in two photons. The mass of what is called the invariant mass of the pair of two photons, which is also the mass of the Higgs particle from which they decayed, is fixed. It's about 126 GeV. This is a discovery. And you see that on a background of many events, photons that are made in very many other ways, there is a little peak corresponding to the creation of something new at a certain mass. And that mass is the mass of the Higgs boson, which is about 125 GeV. It was also observed in other channels, such as the decay through two particles that are called Z's, that were also essentially invented by Shelley, one of which decays, for instance, in an electron and its antiparticle, and the other one in a muon and its antiparticle. And this peak in here is the invariant mass of the four particles, two electrons and two muons, and it corresponds to an object that made them at precisely the same energy or mass, 126 GeV. So those were the discoveries, and these are properties of this particle that agree with the theory. The theory is this line in here, and the theory is this line in here, and you have the probabilities, relative probabilities of decaying into different channels, and they all agree with the theory. So these things, this object that was discovered very, very much looks like the search for Higgs particle. Now, what I've been talking about is called the Standard Model, and it describes the objects that I have talked about as well as their interactions. And there is something that people call beyond the Standard Model. And there are two kinds of things beyond the Standard Model. There are those things that we know exist, but the Standard Model doesn't explain. And there are also these things that we are sorry exist, and we know that they have no explanation and will never have an explanation. I'm going to start by giving an example of one of those. And here it is. And going back to science, I'll tell you why we think that there are things. For our guests, this is our president of the government, who is cutting everything, including science. Now, the study of the microwave background radiation and other things in the sky convinces us that the substance of the recipe with which you make a universe such as ours is fairly simple. You only need three things. One of them is the ordinary matter of which we are made, which in terms of average energy density in the universe is about 4% of the total. There is about 25%, this is an old-fashioned number, it's now 25% dark matter, which is something that acts like matter except that it doesn't emit or absorb electromagnetic radiation. It doesn't have an electrical charge. Electrical charge is the agent of the emission or absorption of photons. It doesn't, but it otherwise acts like matter, and we don't know what it is. It's not part of the Standard Model. And then there is 3/4 of the density of the universe are in something even more mysterious, misnamed the dark energy. Now, how about the dark matter? Why do we know about dark matter? And how about the energy of a vacuum? This is one of the ways. There are 6 or 7 ways why we are absolutely observationally convinced that the universe contains 5 times more dark matter than ordinary matter. This is one of the ways to be convinced. What you see in here is a cluster of galaxies. And you see around it little commas, which are actually galaxies, sometimes the same galaxies seen in different positions. Galaxies that are behind the cluster and whose light has been deflected by the gravity of the cluster and makes you see these multiple images and makes you see what's behind on the other side. And you can compute how much mass is necessary to gravitationally bend this light, and it is about 10 times more than the amount of mass that you see in terms of stars and dust and so on. So there is 10 times more stuff in here than what meets the eye. And that's one of the evidences for dark matter. Dark matter is also one of the things we're looking for at the LHC and not succeeding at finding it. The most fashionable theory, it has been fashionable for so many years, it's called supersymmetry. And supersymmetry is a theory in which for every particle you have another one with a tilde on the head and a slightly different spin. And some particles called squarks would decay into quarks, and brothers or sisters of the photon called photinos. And that would be the objects making the dark matter. But this is something we don't know. We're just looking for it. Now, this is one of the pieces of evidence why we think the universe also contains dark energy. What you see in here is essentially the Hubble plot, something like the apparent velocity of recession of galaxies versus its distance. The distance, this is not galaxies, this is actually supernovae exploding in distant galaxies. And you see that this thing is not linear. It is a little more accelerated at the very distant galaxies. And the reason is that the expansion of the universe, this demonstrates that the expansion of the universe is accelerated. It's currently so that things that have more distance to us have had the time so that we can see that they have been accelerated and not only moved inertially away. So the universe is accelerating in its expansion. And a good question is who is pushing it towards being accelerated? And we think that it is the density of the vacuum. The vacuum is permeated by substances, and therefore it has a density, an energy density. And the energy density of the vacuum, or something very close to it, is the only thing that can exert a gravitational repulsion. That would be the origin of this observed acceleration. And a very interesting point is that there is one measurement and one estimate of the energy density of the vacuum. The measurement is that which I showed due to cosmology. We call the energy density of the vacuum, we should call it the cosmological constant, because after all it was Einstein who invented it with that name, and the symbol for that is lambda. The lambda measured by the cosmological constant measured by the cosmologists is 56 orders of magnitude smaller than the one you would guess from the Higgs mechanism, which is this thing responsible for the existence of the boson and for the masses of the other particles. So this is a disagreement in science by 56 orders of magnitude. It's lovely, it's something wonderful. We know that we haven't understood anything to this level of 56 orders of magnitude. This is one of the best positions in which science could possibly find itself. And that's why there's a big future for young scientists. This is one of the problems they must solve. Now, this is typical in science. When you happen to have come out of a very serious problem like this guy, you find out that by having solved the problem, you have to face an even more serious one, in which case, this one here. And this is a point, and I think it's a good point where I might stop. Thank you.